Hello everyone. In the previous video, we solved the two sum problem using the brute force approach. That solution was simple and used only constant extra space. But because it checked many possible pairs, its time complexity was O(n) square. In this video, we will solve the same problem using a Swift dictionary. The main idea is to replace repeated searching with fast dictionary lookup. For each number, we calculate the value required to reach the target. This required value is called the complement. The formula is target minus current number equal to complement. For example, suppose our target is 9 and the current number is 2. The complement will be 9 minus 2 equal to 7. This means that when the current number is 2, we need to find 7 to complete the target. Instead of searching the complete array again, we check whether 7 is already available in our dictionary. The dictionary stores each previously visited number along with its original index. So, its structure is number with having its original index. For example, 2 is having with its index 0. When should we choose this approach? The dictionary approach is generally suitable when the input array is unsorted. We need to return the original indices. The input may be large. Additional O(n) memory is acceptable. What is trade-off? The dictionary gives us much faster average lookup, but it may store several values from the input. Therefore, we improve execution time by using additional memory. This is known as time-space trade-off. Swift dictionary is implemented as a hash table and is designed to provide fast key-based access. Now, let us look at Swift implementation. Our function receives an integer array and a target value. It returns an optional array of integers because it is possible that no valid pair exists. Next, we create a dictionary. The dictionary key represents a number from the input array and its value represents that number's original index. Then we traverse the array using enumerated. This gives us both the current number and its index. For each number, we calculate its complement. For example, when the current number is 2 and the target is 9, then the complement is 7. Next, we check whether this complement has already been stored in the dictionary. When the complement exists, we already have both required numbers. The dictionary gives us the index of the complement and the lookup gives us the current index. Therefore, we return both indices. When the complement is not found, we store the current number and its index. Then, there is an important detail here. We check for the complement before inserting the current number. This prevents us from accidentally using the same array element twice. For example, suppose the input contains only 1 3 and the target is 6. Then we cannot use the same 3 twice. But if the input is having 3 3 two times in the array, then the first 3 is stored and when we process the second 3, the first one is found correctly. If we finish the loop without finding a pair, we return nil. Now, if we check this program carefully, then we will find out our program's average complexity time is ON. We traverse the array once, and dictionary lookup and insertion are treated as average constant time operations. The space complexity is ON. In the worst case, the dictionary may store nearly all the input values before finding the answer or before returning nil. So, compared with brute force having ON square time complexity and O1 space complexity. Dictionary is having average ON complexity, time complexity and ON space complexity. We are using more memory to reduce the execution time. Now, let us see exactly how the dictionary changes during the execution. So, our input is 2, 7, 11, 15 and our target is 9. So, our first iteration will be index 0 and number 2. We calculate the complement. So, it will be 7. Therefore, we store 2 with its index 0. Now, the dictionary contains 2 with its value 0. For second operation, at index 1 and the current number will be 7. If we calculate complement, then it will be 2. We check the dictionary and 2 is already present at index 0. Therefore, we return the index array 0, 1. The function finishes immediately and it does not need to process 11 or 15. For the standard two-sum problem, the dictionary solution is usually a strong general purpose choice because it works on an unsorted array. It preserves original indices. It provides average linear time performance. The implementation remains relatively simple. However, we should not choose it automatically in every situation. If the input is already sorted, the two-pointer approach can provide ON time complexity with O1 extra space. If memory is extremely restricted, the brute force solution may still be considered. And if we only need a Boolean result, whether a pair exists, a set may be communicate the requirement more clearly. So, the correct solution depends on the input, expected output, memory constraint and performance requirements. In the next video, we will solve two-sum using the two-pointer approach and understand why it works when the input array is sorted. Thank you for watching.